Let's use Euler's method in an example to find an approximate solution for a differential equation. My tablet pen is on the fritz, so if I get a bunch of extra marks on the page, please excuse me. So let's work with this differential equation. dy dx is x squared plus y squared. And remember, we need to start with an initial condition to use Euler's method. So we're going to use y of minus 1 is equal to 0. Remember, this corresponds to the initial condition x sub 0, y sub 0. Our initial condition point is minus 1 comma 0. Okay, and over here are the formulas for Euler's method. Just to identify this function f, remember that is the function that is the right-hand side of the differential equation. So for our particular differential equation, f of xy is x squared plus y squared. Okay, so let's put our x's in this column. So we know x sub 0 is 0. And our y's in this column, so y sub 0 is minus 1. I have those backwards. X sub 0 is minus 1, and y sub 0 is 0. There we go. Now, in Euler's method, to get from one x value to the next, you just add the step size. And for us, the step size is 1/10. So that's h right there. So x sub 1 is minus 1 plus our step size, 0.1. So that's negative 0.9. And then y sub 1 is we take our old y value, that is the y value from the previous line, so that's 0, plus, and now we evaluate our function using the previous x and y values. So we have our x value, minus 1, squared, plus our y value, squared. And then we have to multiply that by h, which is 0.1. So this part right here is f of x sub 0, comma y sub 0. Okay, now we have some arithmetic to do. This whole mess is just 0.1. Okay, so our initial point was minus 1 comma 0. Our next point is minus 0.9 comma 0.1. Okay, now to find our next point, so with x sub 2 and y sub 2, we do the whole thing again, but instead of using our initial point, we use the point we just got. So always, each round through Euler's method, you never go back to the original point. You always use the point that you just generated. So x sub 2 is x sub 1, which is minus 0.9, plus our step size, which is 0.1. So that's minus 0.8. And then y sub 2 is the y value from our previous steps, so 0.1, plus, and then we evaluate the function f using the point from this previous step. So minus 0.9 squared plus 0.1 squared, all times 0.1. Okay, dump this whole mess into a calculator and you get something like 0.182. Okay, plus some other digits probably, but since we're finding an approximate solution, we kind of have to pick a point to round to and just round to that place, because we can't pretend as if we have infinite precision because it's an approximate solution. So our next point is minus 0.8 comma 0.182. All right, so we're trying to get an approximate solution on the interval from minus 1 up to minus 0.5. This is in the x direction. So we need to keep going, right? We have to keep going until we get a point where the x value is negative 1/2. So our next one, x sub 3, is our previous x value, minus 0.8, plus the step size, 0.1. That's minus 0.7. And our next y value, y sub 3, is y sub 2, 0.182, plus, and then we evaluate our function. So the x value squared minus 0.8 squared plus 0.182 squared, and all of that times 0.1. Notice that we're using the previous x value here and the previous y value. It would be a mistake to use our new x value that we just found. So don't accidentally use that when finding your subsequent y value. Okay, so now we can evaluate all of this. We got something like 0.2493. So this is negative 0.7, comma 0.2493. All right, looks like we're going to have to do 2 more. So I hope you get the feeling that this is sort of a very mechanical process that doesn't really require a lot of thought. That's absolutely true, right? Once you've done Euler's method a few times, doing it again is incredibly boring, right? The inspiration for Euler's method is very geometric, but actually grinding through the calculations is a bit of a drag. So negative 0.7 squared plus our previous y value, 0.2493 squared times 0.1 equals, this time we get 0.3045. So our next point is minus 0.6, comma 0.3045. Okay, this next one's going to be our last one because we're going to finally have an x coordinate that is minus 1/2. So negative 0.6 plus 0.1 is negative 0.5. And then our last y value is 0.3045 plus, then evaluate our function. So negative 0.6 squared plus 0.3045 squared, all times 0.1. And this gives us 0.3498 when we round that. So our last point is minus 0.5, comma 0.3498. Okay, finally. So we have all these points. To actually get sort of an idea of what this would look like, let's look at all of these points graphed on the slope field for this differential equation. So here we go. I've asked GeoGebra to give us a slope field for this differential equation, and I've plotted the points that we just found right over here. You can see we're starting at minus 1, comma 0, and we end up at minus 0.5, comma something. It looks like about maybe 0.3 or 0.4. Of course, we know that it's actually 0.3498. And remember, what we're looking for is at every little line element, at every tick mark that these points touch, the solution should be tangent to those tick marks. It's a little hard to tell as it stands right now because we're zoomed so far out. There just aren't very many tick marks. But if you zoom in, right, GeoGebra automatically adjusts all the slopes of the tick marks. And if we can even position the xy plane so that our initial point is right on top of one of those tick marks, you can kind of eyeball what a solution would be. It looks like it's going to be about, something like this. Right. After that, we don't really know. We could follow the tick marks or do Euler's method a few more times to get a better idea. But the thing to notice about this is that this graph that we're drawing is roughly tangent to all of the little line elements that we're passing near. So that's sort of verification that we didn't make any gross arithmetic errors when we were doing Euler's method.